Well, hello and welcome to our Advanced Routing Deep Dive. My name is Kevin Wallace, and I'm thrilled to have you here with us. And it's been a while since we've done one of these deep dives, and I was noticing the attendance, the registration numbers. It's kind of interesting that the more introductory level things like maybe subnetting, something like that, that doesn't get near the attendance as the more advanced training. Like we did a VPN deep dive and got huge attendance. We've got about 2,000 people registered for this advanced routing deep dive. So yeah, going forward, we might want to focus on some of the more in-depth, higher-end technologies. But let's take a look at exactly what is on our agenda today. I think you're really going to enjoy today's session. We've got lots of demos planned for you, and we're going to be taking a look at three different advanced routing concepts. And the first one, and this is from a student request from a previous deep dive, somebody asked if we would do route redistribution. I thought, that's a great idea. And in addition to route redistribution, I thought we'd do a few other things as well. But we're going to begin today with the fundamentals of route redistribution, and we'll take a look at how to do configuration of mutual route redistribution. Maybe we've got a couple of companies that merged together. One company was running OSPF, one company was running eEdge ERP, and now they're trying to share the same network. How can we support that? We'll take a look at that. And there's a lot that can go wrong. And we're going to take a look at some different ways of troubleshooting route redistribution. We'll get into setting things like tags when we go from one autonomous system into another autonomous system. I think you'll really enjoy that one. So lots of demos coming up today. And after that first of three technologies, route redistribution, we're going to take a look at IP SLA, Service Level Agreement. And this can help us out in a couple of ways. One of the things that IP SLA does is it can send probes out into the network to sort of test the waters, to see what the network is like. How is the network treating this packet? Does it have too much delay? Does it have too much jitter? Am I dropping too many packets? This can tell us how the network conditions are. And based on that, we can get some statistics sent back to us. We can configure a far-end router as what's called a responder, and we'll do that today. And that responder can measure things like delay, jitter, packet loss. And that's one demo we'll do. We'll see how to set up that measurement aspect of IP SLA. But we can also use IP SLA to actually make routing decisions. We could say, I've got two paths to get to this destination, but I prefer to go this path. It's got more bandwidth, but sometimes it's congested and there might be too much delay on this link. So we can have sort of like an if-then statement. If there's too much round-trip delay going this way, then I'm going to go this way. And we'll see how to set that up as well. And speaking of overriding the routing table and making our own decisions, we're going to wrap up today with a look at PBR, policy-based routing. Before a router consults the IP routing table, or the CEF fib more accurately, to make its packet forwarding decision, it can see if there is a policy applied to an interface. And if there's a policy applied, that policy is going to dictate how we forward that packet, not the CEF routing table. So we'll see how to set that up as well. And of course, we'll give you a demo of that. And if you're new to me, if you're new to my world, you just found me on YouTube perhaps, here's a super quick bio because I'm guessing we're going to spend about 2 or 3 hours together today. So here's my quick background. Again, my name is Kevin Wallace. I've got a couple of CCIAs, one in enterprise infrastructure, one in collaboration. I've been doing this for a while. I've had my CCIA for over 20 years, so I've reached the lifetime Emeritus status. I don't have to requalify anymore, which is awesome. And I've been working with Cisco gear since the very first model of Cisco router, the old Cisco AGS Plus router back in the late 1980s. And I worked for Cisco Learning Partners for about 14 years, teaching lots and lots of Cisco training. And from the real world perspective, I was a network manager at a university. One of my favorite jobs, I would have to say, was down at Walt Disney World. I was one of 5 network designers down there. I actually got to design and help implement the upgraded network that ties together the Magic Kingdom and Epcot and the studios and Animal Kingdom and a bunch of the resorts. They're just an amazing place to work. Written a bunch of books, done a bunch of videos for the folks over at Cisco Press, been a speaker at Cisco Live. The bottom line is, I love this stuff. And I cannot wait to dive into some of these more advanced technologies with you today. And I want to give you let's call it an ethical bribe to stick around to the end. If you'll stick with me to the end, I've got a gift for you. Here's what I mean. If you hang out to the end, I'm going to give you a link where you can go download a zip file. And this zip file is going to contain some very detailed PDFs. I created these yesterday. And these PDFs have the base configuration for each of the routers in our topologies. It has a picture of the topology. So if you're using your own gear, or you're using GNS3 or EVNG or whatever, you can take that and reconstruct the topologies that we're going to be doing here in a few moments, that we're going to be working through. And then I've got a step-by-step script of how to do all of the demos that we're doing today. These are very lengthy PDFs, and I've got one for each of our demonstrations. And if you happen to be using Cisco Modeling Labs, CML, I'm also going to include in that zip file a .yaml file of each of the topologies. So if you can import the YAML file, that'll save you a couple of steps of having to build the topology on your own. And if you've worked with CML, you know how YAML files are. Depending on your version of CML and the version I exported from, which is 2.6 by the way, it might work, it might not. So if it works, great. If not, I've given you all the base configs so you can set things up on your own. Now, if you're ready, I'm ready. Let's get into it, shall we? The first of our three major topics is route redistribution. And route redistribution is when we have a couple of routing protocols or routing processes or really autonomous systems. An autonomous system, we always say, is a network under a single administrative control. And if these two autonomous systems are running different routing protocols and they need to exchange routes between themselves, how do we do that? Well, we can do that if we have more than one interior gateway protocol in our enterprise. We can do that through route redistribution. Why would we have more than one interior gateway routing protocol in our enterprise? Well, maybe a couple of companies merged. One company was running EIGRP, one company was running OSPF, and suddenly they have to coexist peacefully, hopefully, on the same network. Well, we could do route redistribution to make that happen. There's a challenge, though. Here I'm using EIGRP and OSPF as an example, but if you think about the metrics, in fact, go ahead and type it in the chats. What does OSPF use for its metric? What does OSPF use for its metric? Yeah, it's cost. Cost is a function of bandwidth. Now, by default, and I emphasize by default because you can play with K values and do some other stuff, but by default, what does EIGRP use for its metric? Well, it considers bandwidth and delay, and bandwidth being the bandwidth of it's representative of the slowest link between point A and point B, and the delay is cumulative. We add some delay as we exit each router. They're very different measurements. It's like apples and oranges. How do I take a metric from from OSPF and make it meaningful to EIGRP and vice versa? Well, what we're going to be able to do is, as we're redistributing, we can assign a metric. I can say, for example, everything that I'm injecting into OSPF, I'm going to assign it a metric of 30, we'll say. And for EIGRP, I will have to be a bit more specific. I'll have to give measurements for bandwidth, delay, load, reliability, MTU. The acrostic that I always use is big dogs really like me. The B in big reminds me of the B in bandwidth. The D in dog reminds me of the D in delay. The R in really reminds me of the R in reliability. The L in like reminds me of the L in load. And the M in me reminds me of MTU. So big dogs really like me. Bandwidth, delay, reliability, load, and MTU. Another reason we might need to do route redistribution is we have different departments within our company that have their own way of doing things in the network. Let's say that we've got research and development, and they're very techie people there, and they want to do their own thing, and they don't want to conform to what the rest of the company's doing. So they're insisting that they run intermediate system to intermediate system in their department. But everybody else is running EIGRP, for example. Well, that would be another reason we might want to do that mutual route redistribution. Or sometimes we're dealing directly with the partner. We're doing a lot of communication, a lot of file exchange directly between two parties, two different companies. Yeah, I'm not going to ask my partner company to adapt to my routing protocol. And quite honestly, I don't want their OSPF database to be merged with my OSPF database. I'd like to keep those separate so we could redistribute even between a couple of OSPF autonomous systems. That'd be another reason this would come in handy. Or maybe we're connecting out to multiple service providers. And we typically use BGP. That's an exterior gateway protocol to do that. And we might be learning the full internet routing table. And if I need to advertise BGP routes, I might leak a few routes in, maybe not all of them, because there's like 900,000 right now. But if I leak some of those routes in and I send some of my routes out to the internet, that can be done through route redistribution. Now, the command we're going to be using is the redistribute command, and we're going to give that command inside of router configuration mode for a particular routing protocol. And we're going to say, or we're going to inherit a default setting called a seed metric of what the metric is going to be for routes that we're injecting into that routing protocol. So if I'm in router configuration mode for OSPF and I say redistribute EADGRP and give an autonomous system number, I need to say, or I can take the default value for what the metric is, the OSPF metric, for all those routes I'm injecting from EADGRP into OSPF. And some of our routing protocols have an undesirable default metric. And by that I mean it's considered to be infinity. So again, a seed metric, that's the default metric that we have for a routing protocol. So if I'm injecting, let's say I'm injecting RIP or EADGRP into another routing protocol. I'm injecting it into OSPF. Notice the default seed metrics for both RIP and EADGRP. I'd like you to memorize these, by the way. This is critical to know for the real world as well as for exam purposes. But their default metric, their seed metric, is infinity. Any networks you redistribute from EADGRP into OSPF, if you don't specify what the metric is going to be, they're not going to be advertised. They're going to be considered as unreachable networks because their default metric is infinity. Now, that's not the case if I'm redistributing something into if I'm redistributing something into OSPF. Now, I think I said that backwards. If I'm redistributing into RIP, the default metric is infinity. If I'm redistributing into EADGRP, the default metric is infinity. If I'm redistributing into OSPF, then the default metric is 20. Or, slight exception, if I'm redistributing BGP into OSPF, the default metric is going to be a 1. So think about the protocol into which you're injecting these routes and make sure you've got an appropriate metric for those routes that you're going to be redistributing. Now, BGP is kind of different because BGP doesn't just have one thing that it looks at when it's trying to make a routing decision. Remember the acrostic, "We love oranges as oranges mean pure refreshment"? Have you ever heard our training on that? The W in we is the W in wait, and the L in love is the L in local preference, and it just goes on and on. But the point is, there's not just one thing that BGP considers. So what kind of metric do we assign to routes being injected into BGP? Well, it's going to take on whatever metric value the protocol has that's being injected. So EADGRP might have a value of 2.5 million while OSPF has a value of 3. Does that matter? Probably not, because when we assign that metric to BGP, we're assigning it to what's called the multi-exit discriminator, the MED. That's considered to be the quote-unquote metric for BGP. But that's not even considered unless we have a bunch of ties and things like wait and load and origin type and autonomous system path. It's probably not going to get to that, but that's what's going to happen. If you go look at your table, there's going to be a column for metric. That's the MED, the multi-exit discriminator. It's going to have OSPF's metric, or EADGRP's metric, or RIP hop count. That's going to be assigned to that MED value in BGP. The big takeaway from this slide is if you're redistributing into RIP or you're redistributing into EADGRP, you need to specify the metric that you're going to assign those routes you're redistributing into those protocols. Otherwise, those routes are going to be considered to be unreachable. Now, I mentioned that we're going to use the redistribute command to do this. And a lot of times it's hard to visualize. I'm in EIGRP router configuration mode and I say redistribute. Am I saying I want to redistribute EIGRP into something else? Or am I saying I want to redistribute something else into EIGRP? Well, it's the latter of those. If I say redistribute inside of EIGRP router configuration mode, then I'm redistributing something into EIGRP. I'm redistributing it into the router configuration mode that I'm in right now. And there are 3 ways to do that we're going to demonstrate today. Number 1 is I can set a default metric. That applies to every route that I'm redistributing into this routing protocol. So if I'm in EIGRP router configuration mode and I say redistribute OSPF and redistribute RIP and redistribute ISIS, I can assign a default metric that will be assigned to all of those routes being redistributed from all of those routing protocols. And that's an easy way to do it. If we want a little bit more granularity, maybe I want to give OSPF routes that I'm redistributing into EIGRP, I want to give them one value, and RIP routes, I want to give them a different value. We can specify the metric as part of the redistribute command. And I'll do that for you live as well today. And finally, if we want to get really advanced, we can use a route map. We'll be using route maps a few times today. So let's take a pause for a second and think about what a route map really is. A route map can match traffic based on maybe an access control list. There's different ways to match based on packet length. And once we match that traffic, we can set a parameter. That parameter might be the next top gateway. That parameter might be a tag that we're stamping on that particular packet. We'll take a look at that. And it could be the metric as well. Now, what we want to do now is go out to our live interface and configure mutual route redistribution between a couple of autonomous systems. Let me bring up a topology, and I'll take my face off the screen so I'm not taking up that valuable real estate. And let's configure mutual route redistribution. Now notice that R2 is sitting at the boundary of these 2 different autonomous systems. We've got an interface in OSPF and we've got an interface in EIGRP. And I'm sitting on router R2 right now. And if I want to see what routes we currently have on router R2, I can say show IP route. And let's see what we have. If we see a route with the O code, that means I've learned it via OSPF. By the way, we also see the OSPF metric here of 2. This is the administrative distance, the believability of the routing protocol. It's 110. If we see a D, that means I've learned it via EIGRP. Now why a D to represent EIGRP? It's the algorithm that EIGRP uses. It uses an algorithm called dual, D-U-A-L. That's the diffusing update algorithm. That's why we have a D here. But here we see a couple of routes that I've learned via EIGRP. And we see that EIGRP uses a very different way of calculating a metric. We might be in the thousands or tens of thousands, or even I've seen the millions plenty of times. So it doesn't really compare directly to OSPF, which might have a 2 or a 3. And we see the administrative distance of EIGRP, it is a 90. So it is considered more believable than OSPF. So here's something to think about. If a router is receiving updates from both an EIGRP neighbor and an OSPF neighbor, and it's an update for the same route, who's it going to believe? Yeah, it's going to believe EIGRP. That might be an issue for us. We'll talk about that. Now let's see if our other routers have knowledge of any other networks. Let's go over to router R1. That's strictly in OSPF. If I do a show IP route here, we're going to see that it doesn't know about any routes that it's not directly connected with. What about R3? Let's do a show IP route. Same thing. It doesn't know about any routes to which it's not directly connected. Well, let's fix that. Let's configure mutual route redistribution. And Remember that I said EIGRP had a default metric of infinity. So when we're injecting a route into EIGRP, we need to specify the metric. Just to prove that, I'm going to leave that step out at the beginning of this. I'm deliberately not going to specify a metric for EIGRP redistribution or redistributing into EIGRP, just to show you that it's not going to work, and then we'll add that metric. But on R2, let's go back to R2. That's where we have to configure route redistribution, because that's the router connected to both autonomous systems. Let's go into global configuration mode, and then into router configuration mode for OSPF process ID 1, and I'm going to say redistribute EIGRP, and the autonomous system number is 1. And let's do the same thing for EIGRP. I'll say router EIGRP autonomous system 1, and I'll say redistribute OSPF process ID 1. And let's think about what we just did. Well, one thing, if you've been doing this for a while, you might say, uh-oh, Kevin, you forgot to give the subnet's keyword. Yeah, in some older versions of Cisco iOS, if I had given this command under OSPF router configuration mode, if I had just said redistribute EIGRP 1, that would only redistribute classful networks. So if I had subnets that I wanted to redistribute, it wouldn't work. But in more recent versions of Cisco iOS, the subnets keyword is included. It's added by default. You might want to make sure that's the case, or you might just always want to give the subnets keyword. I deliberately left it out so I could show you that it does get added in this version of Cisco iOS. I think I'm running 15.9. But let's prove that. Let's do a show run. I'm going to pipe that to section router OSPF1. I did not type in the subnets keyword, but notice it got added by default. That's not going to happen on some of the older versions of Cisco iOS, so be cautious of that. Now, let's see if we have learned any routes now that we've done this route redistribution. Let's go over to R1, which is in OSPF. When we redistributed into OSPF, remember from that table, OSPF had a default metric of 20. Let's take a look. Let's do a show IP route. And you'll see these O routes. These were learned via OSPF from router R2. Their metric is 20. And notice the E2 tag right there. The E2 tag means that this is an OSPF external type 2. Now there is also an OSPF external type 1. And personally, I'm a favorite of type 1. Let me, well, I was going to explain this later, but now's as good a time as any, I suppose. Here's the difference. With when we're redistributing into OSPF, by default, we're going to use those external type 2 routes. Excuse me. And what that means is whatever metric gets assigned by my autonomous system or by my ASBR, my autonomous system boundary router, that metric is going to go throughout OSPF unchanged. So if I redistribute, excuse me, if I redistribute with a metric of 20, then if it goes through one router and a second router and a third router, it's still going to have a metric of 20. That doesn't seem accurate, does it? That's type 2 routes. So it keeps the value assigned by the ASBR throughout OSPF. Now, it's not a big deal here. We've only got one way to go out of OSPF, so it really doesn't matter. If we're trying to get to one of those external routes, we've got to go through R2. So it doesn't matter that they all have the same metric. However, if I have a more complex topology, where maybe I have a couple of ASBRs, I've got more than one way to get out of OSPF, this could be a problem. Because one route might actually be better, but all my routes are showing the same metric. What we can do is say, instead of using type 2 OSPF routes, external routes, let's use type 1. Type 1 will take the value assigned by the ASBR and it will add cost for each router hop, just like OSPF would do normally. So if I go over a gig link by default, that's a cost of 1. So if I redistributed into OSPF with a type 1 external route, it would be a 20. That's what the ASBR set. And then to go from R2 to R1, that would be a cost of 1 over that gig link. I'd have a cost of 21 showing up on R1, but right now I don't. It's just a cost of 20. I'll show you in a few moments how to fix that. I think it's a better practice. It's more accurate. So I'm not quite sure why the type 2 is the default. Now let's go over to R3. On R3, let's do a show IP route. And no surprise, we have not learned any routes. And the reason is when we injected those OSPF learned routes into EIGRP, they were injected with EIGRP's default metric of infinity. So they're considered to be unreachable. They don't show up. What we have to do when we're injecting into EIGRP is assign a metric to those injected or redistributed routes. And I mentioned a few moments ago, there are 3 ways that we could do that. One way is to set a default metric for all of the routing protocols that we're going to be redistributing. And that's what we'll do at the beginning. But we could also give that metric as part of the redistribute command if I want to give different metrics for different protocols that I'm redistributing. Or I could use a route map. I'm going to show you all 3. Let's go back over to R2. I'll start with the simplest one, and that is to set a default metric for everyone. Let's go back into router configuration mode for EIGRP Autonomous System 1. And I'm going to say default -metric. And remember the acrostic big dogs really like me, bandwidth, delay, reliability, load, and MTU. I've got to specify values for all 5 of those. So let's use some context-sensitive help. It says, what is the bandwidth? And the unit of measure is in kilobits per second. Well, in my case, this is a gig link. How many K is 1 gig? 1,000,000. So I'm going to give 1, 2, 3, 1, 2, 3. I'm going to give a value of 1,000,000 as my bandwidth. Next up is delay. Now this is an interesting one. The unit of measure is not microseconds or milliseconds. The unit of measurement is tens of microseconds. And I'll say 1. Minimal delay there. Next up is reliability. And reliability is represented sort of as a fraction. It's some number over 255. Well, and we're specifying the numerator in that fraction. If I'm 100% reliable, and I hope I am, then that numerator would be 255. So we would have 255 over 255, that's 100% reliable. So my reliability is 255. The load is also a fraction with 255 as the denominator. And if I'm minimally loaded, then that number is going to be a 1. So I'm very reliable and I'm not loaded. We'll make that a 1. And then finally, what is the MTU? The maximum transmission unit. I'll give the default of 1500 bytes. And that's going to be my default metric. Now, at this point, we should be redistributing those routes into EIGRP and we would put these values into the EIGRP metric formula, which we've talked about in some other training. MTU, by the way, does not show up in that formula. That's designed as a tiebreaker, but all the other values do. But many of them are zeroed out thanks to the default K values. We're only considering bandwidth and delay by default. But while we're at it, I wanted to do one other thing while we're here on router R2. Let me go back into OSPF router configuration mode really quickly, and I want to set its default metric to something else. Let's set it to 30 as an example. Let's change it from the default of 20. And we'll verify that in a few moments. But for now, sticking with EIGRP, let's go back over to R3 and see if we have now learned some of those EIGRP routes. Let's do a show IP route. Great news, look at this. You see we have a D representing EIGRP learned routes, and the EX means that these were learned from an external source. They did not originate inside of EIGRP. They are EIGRP external routes. And you might remember from your studies of administrative distance that EIGRP is fairly intelligent about this. It's going to give a different administrative distance value for internal EIGRP, which is 90, versus external EIGRP, which is 170. External routes are not going to be as believable. And we can see that here. We can see that we've got a default AD of 170. So we know these came from external to this autonomous system. But great news, we now know how to get to everywhere in this entire topology. That's great. Let's see how to do this metric assignment a second way. I said I would show you all three ways. On R2, let's go back and in router configuration mode for EIGRP Autonomous System 1, I'm going to say no default metric to get rid of that. And I'm going to get rid of my redistribute command, no redistribute OSPF1. And I'm going to put the redistribute command back, but as part of that redistribute command, I'm going to specify the metric. Let's say redistribute OSPF1 metric. And again, it's going to walk me through those 5 different parameters for an EIGRP metric. I'll give the same values I did before. 1 million for the bandwidth, 1 for the delay, 110 microsecond unit. We'll give 255 for the reliability, a 1 for the load, and 1500 as the MTU. Will this work? Let's go check it out. Let's go back over to R3 and once again do a show IP route. Do I know about those routes? Yes, I do. We still have those 3 routes that were redistributed into EIGRP. There's one other way to do it, and that's using a route map. Now let's go back over to R2 and talk about a route map. Let me undo what I just did. Let me say router EIGRP1, and let's negate what we did. I'll say no redistribute OSPF1, get rid of that, and let's set up a route map. And the route map typically is going to match certain traffic, and then based on that traffic that we match, we're going to take an action. We're going to set a parameter for that traffic. Well, here, I want this to apply to all traffic. I'm not trying to selectively assign a metric. I want to assign a metric to everything being redistributed from OSPF into EIGRP. So I don't really have to match anything this time. This is going to be a very basic route map. I'm going to say route -map, and I'll just give it a name. When I give a name for a route map, I like to make it all uppercase. That way, when I'm looking through the configuration, I'll see something that's all uppercase, and that tells me immediately, ding, 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 that's not some sort of a special iOS keyword. That's a name that I made up. So I'm going to make it recognizable to me by making it all uppercase. Set metric set metric demo. And I'm not going to match anything right now, because I want to apply this to all OSPF routes being redistributed into EIGRP. I'm just going to set something. I'm going to say I want to set, and there's lots of things we could set. I'm going to set the metric. And I'm going to set the metric to the same value we've been using, which is 1 million, 123, 123, followed by a delay of 1, followed by reliability of 255, followed by a load of 1, followed by an MTU of 1500. Now let's go back into router EIGRP Autonomous System 1, and let's reissue that redistribute command for OSPF1. But now I'm going to apply the route map called set -metric -demo. Let's see if that worked. Let's go back over to router R3. And once again, let's say show IP route. Great news. We still have those 3 EIGRP learned routes. Now, remember what I did a few moments ago? Just for fun, I set the OSPF default metric from its seed metric of 20. I set it to a 30. Let's go over and make sure that the routes on R1 now have a metric value of a 30. Let's do show IP route on R1. They were 20, and now they're all 30. And they're using this type 2 external OSPF route. And I made the case earlier that I'm a big fan of type 1. It's simply more accurate. So let's see how we can make these redistributed routes be type 1. To do that, let's go back over to R2 and back into router configuration mode for OSPF process ID 1. Let's get rid of our previous redistribute command. No redistribute EIGRP1. And now I want to say redistribute EIGRP1, but I'm going to set the metric type to type 1, external type 1. Now, let's go over to router R1, and not only should we still have, well, we should have a couple of things that are different. This 30, that was the value that was set by R2. That's the value assigned to these redistributed routes by the ASPR, which is R2. And with type 2 routes, that number doesn't change. It doesn't matter how many routers we go through, that number does not change. But I think it should, because we're actually adding cost as we go through other routers. And what we should see now, we should see this be the 30 that was set by R2 plus the cost it takes me to get from R1 to R2. This is a gig link. By default, that has a cost of 1. So I'm going to expect to see a metric value of 31. And this E2, that should be an E1. Let's take a look. Now look at this. Now we have type 1 external OSPF routes. And we have, I think, a much more accurate metric value of 31. So that's a look at how we can do mutual route redistribution between a couple of routing protocols. And we could run into some issues, and I want to discuss a few of those issues with you. Let's talk about troubleshooting route redistribution. What could go wrong? Well, let me give you two of the most common issues we have when troubleshooting route redistribution. One is, well, in fact, I demonstrated this one. We're trying to redistribute into a routing protocol that has a default metric or a seed metric of infinity. What are those? Those are RIP and those are EIGRP. Remember what happened? I didn't initially set a metric for routes being redistributed into EIGRP. It took on the value of infinity, and those routes were not learned by R3. So that's one common thing that we've already seen how to address. Something that's a lot trickier sometimes, especially in larger networks, you've got multiple ASPRs, you might have multiple routing protocols, you might have some static routes involved. In really complex topologies, you can get into sort of a looping condition. Let me give you an example of what I mean by a looping condition. Let's say that R2 and R3 over there, and I didn't put protocols on these because it could be RIP, it could be ISIS, it could be EIGRP, we might have some static routes, it could be some floating static routes. Just in general, here's what might happen, and here are some ways that we might deal with this. But R2 and R3, if they're talking to one another, they should go directly between one another. They're in the same autonomous system, whatever that is. But let's say that R2 has advertised a route up to RD1. And that's going to redistribute it into the blue autonomous system. So it's going to go to R1. R1's going to advertise it to its neighbor, RD2. And RD2 is going to advertise it to its neighbor of R3. Now, let's say that when RD2 redistributed that to R3, it gave it a lower metric than the value learned from R2. So in other words, R3 might prefer to go to RD2 and then to R1 and RD1. It's going way out of the way. It's going to be a suboptimal path. One way to address that is simply to set a higher metric. We could say when I'm redistributing into an area, I don't want to be the most attractive route. Or into an autonomous system, I don't want to be the most attractive route. So yeah, I could set an artificially really, really high metric. Something else we might want to do, and this isn't needed that much, but you might have a situation where something is being learned via, let's say, OSPF when it really should be learned via RIP, but OSPF is more believable than RIP. The bottom line is you might have a condition where you might want to change the administrative distance of a protocol. You might want to make OSPF more believable than EIGRP. Let's see how to do that. Let's go back out to the live interface really quickly. And let's see. Let's go back over to R2. And let's say that we want to change the administrative distance for OSPF. The default is 110. So if I do a show IP route on R2 right now, you're going to see that the administrative distance for these OSPF learned routes, 110. But I could say I want to go into router configuration mode for OSPF process ID 1, and I could say distance. If I could spell, that would be helpful. Distance, and that is the administrative distance, and I'm going to set it to 80. Now if I do a show IP route, look at that. Now, instead of having the default administrative distance of 110, now it's an 80. Suddenly, OSPF on this router anyway is more believable than EIGRP. Not saying that we should do this very often, and I'm having a hard time coming up with a specific instance where we would need to do this. Just a tool for your tool belt. If you're running into a looping issue, this is one thing you might consider. You could change the default administrative distance. Something else you might do is filter those routes. When we did our deep dive into, let's see, OSPF, we've done a deep dive into EIGRP and OSPF was more recent. We talked about route filtering. We saw that we could filter routes at the ASBR, the ABR. We could filter it as it went from the IP routing table into the OSPF rib within a router. Yeah, you could simply say, I'm going to filter those routes out so they don't get specific routes don't get re-advertised into OSPF. Or my favorite approach that I think is really clever is to assign a tag. Here's what I mean by tag. A tag is an attribute that we can sort. It's like you rubber stamp a value on these packets, and it's called a tag, and it can be a number. And let's say that I don't want routes from. Let's pretend that the orange autonomous system is EIGRP, and the blue autonomous system is OSPF. And I don't want EIGRP routes to go out to OSPF and then back into EIGRP. So what I could do is, as I'm redistributing those routes from the orange autonomous system into the blue autonomous system, I could say, I want to set a tag on all those packets to a 10. So rubber stamp, 10, 10. They all have a value of, or a tag of 10. Then, as I'm redistributing from blue into orange, down on RD2, I could have a rule that says, I want to deny any packet that has a tag of 10. So we set a tag of 10 going out, and then we don't allow those marked packets, those tagged packets, to come back in our autonomous system. Let me show you how we could set that up. Let me go full screen again, so you can see this just a little bit better. And on R2, here's what we could do. Now, again, here's the goal. We want to assign a tag of 10 for routes or for packets being redistributed from EIGRP into OSPF, and then we want to block any routes with a tag of 10 from being redistributed from OSPF back into EIGRP. That might prevent a routing loop for us. Here's how we can do that, and we're going to do it with route maps. I'm going to say route map. And let's create one that's just going to mark everything. It's going to rubber stamp all these packets with a tag of 10. I'll give it a name of tag 10. And here I'm applying it to all these packets that are being forwarded. So I don't need to match anything. I just need to set something. I'm going to say set. And one of the many things we can set is a tag. I'll say set the tag to a value of 10. Okay? That's one route map. Now let's create another route map that I will apply as we're redistributing back into EIGRP. And that tag is going to say, or that route map is going to say, if something is marked with a tag of 10, deny it. Don't let it in. Now here, I actually do need to match. As I've been saying that a route map can match something and then set something, but I haven't actually matched anything yet. Well, we're going to do that now. I'm going to say route-map. And I'm going to call this deny tag 10. And I want to deny anything matched with a tag of 10. So I'm going to say right here, kind of like an access control list, I'm going to say deny. Now, don't get thrown by this number. I said deny 10. I'm not saying deny a tag of 10. That 10 is a sequence number. Kind of like access control lists. It's an ordered list of access control entries, an access or ACEs as they're called. and they each have a sequence number, and we start at the low sequence number and we go up. Well, I want to deny anybody that has a tag of 10 first. So I'll give it a sequence number of 10. Then I'm going to create another rule that says permit everybody else. I don't want to block anybody else, just those packets that have a tag of 10. And I'll give that a sequence number of 20. If I gave that other rule first, it would permit everyone before I had an opportunity to deny those packets with a tag of 10. So that 10 right there that I just gave, not a tag value. That's a sequence number value. I'm going to say deny tag 10. And what I'm going to match that's going to be denied is I want to match a tag value of 10. Now there it really was talking about the tag value. Now let's create a second entry with a sequence number of 20 this time. I'll say route map deny tag 10. This time I want to permit everything else. I'll say permit, and I'll give a sequence number of 20. And I don't need to match anything because I want it to apply to everyone. So that's really all I need to do. I think I'm done with my route map. I can say exit out of that. Let's go into router, OSPF configuration mode. And this is where we want to rubber stamp those packets with a tag of 10. I'm going to say redistribute, EIGRP1, route-map, tag 10. So this is going to mark traffic from EIGRP into OSPF with a tag of 10. Now let's go into router EIGRP configuration mode for Autonomous System 1. And I'm going to get rid of my redistribute command, or I'm going to override it. So I'm going to set a default metric like we did before. I'll say default -metric, and I'll give the same values 1 million, 123, 123, and we'll say delay of 1, reliability of 255, a load of 1, MTU of 1500. Now, I'm going to say redistribute OSPF process ID 1 using the route map of deny tag 10. So it's only going to deny things that have the tag value set to 10. It's going to permit everyone else. And that's another approach for how we might troubleshoot a route redistribution configuration. Well, I hope you enjoyed that fairly lengthy demo. Here in route redistribution, we've talked about how to do mutual route redistribution. We talked about the concept of a seed metric. That's the default metric that a routing protocol will assign to routes being redistributed into that protocol. Two of our routing protocols, RIP and EIGRP, had seed metrics or default metrics of infinity. So if I'm redistributing into those protocols, then we'll need to set a metric value. Otherwise, it's not going to work. Welcome back from the break, everybody. Let's jump into our second of 3 advanced routing topics. And this one is IP SLA. And SLA, that stands for Service Level Agreement. I don't think the name really does justice to what this feature can do for us. I first came across this IP SLA feature in the voice world. I do a lot with Cisco collaboration, and sometimes with collaboration and you're placing voice and video calls, you want to make sure that the path you're using to get to a destination phone, an IP phone, is a good connection. We're not dropping packets. There's not too much delay. There's not too much jitter. By the way, jitter, that's the gaps between your voice packets. So you send a voice packet, and maybe there's a big data packet next, and then there's another voice packet as part of that same voice stream. Well, if the reception time of those two voice packets has a gap of more than 30 milliseconds, that can start to cause some quality issues. So we want to minimize jitter. Cisco says try to keep it below 30 seconds. But what this can do, what I used to do with IP SLA is, and it used to be called something else back then. It used to be called RTR, the response time reporter, or the real time responder, some of the literature called it. But it can send a probe out into the network. You can make a packet look like a voice over IP packet. In fact, I'll do that for you here in just a few moments live. But we can make a packet look like a voice packet or a variety of other packet types and see how the network treats it. And that's one thing that IP SLA can do. It can measure network performance. It can tell us how much jitter we're experiencing. And I'm kind of fond of using it for voice over IP or collaboration purposes because that's when I first used it. And it can even give you a measure of the quality of a phone call. We talk about in my collaboration training, we talk about a grade called the MOS, the Mean Opinion Score. And the mean opinion score ranges up to 5. 5 is like perfect surround sound. It's like you're in person. There's no degradation of voice quality at all. Anything of a 4 or above MOS is considered to be toll quality voice. Well, we can see the quality of a voice call. This will actually give us that measurement, which I think is just super valuable. Something else it can do, we can use it to make routing decisions. We can say, yes, I'm going to measure the performance of this link, and if it's not good enough, if the delay is too much, then I'm going to start routing in a different direction perhaps. Let me give an example. Let's say that I want to see how voice over IP traffic is being treated in this network. Well, what I could do is I could set up an IP SLA operation. We define an operation, and I can say in this operation that I want to mimic an RTP, a real-time transport protocol packet, and I want to measure the jitter, that inter-packet arrival time, hopefully keeping it under 30 milliseconds. And I'll say how often I want to send it out. Maybe I send a packet out every 5 minutes. Maybe I send it out. I'll do 30 seconds today because just to make sure we send out plenty of packets and we're able to see some data. But maybe in the real world during business hours, I want to send out a probe every 5 minutes. Let's go out to live interface and take a look at 2 different examples. First, I'll do what's called an RTR example. That's the response time reporter. Let me pull that topology up for you. Let me show you the topology we're going to be working with. And then I'll give you a different topology. And in that topology, we're going to be making a routing decision based on network performance. But here, we're going to use what I call the RTR feature of IP SLA because it used to be called Response Time Reporter or Real-Time Responder. And what we can do is in this case, we're going to make router R2 our responder. We're going to be sending traffic from R1 to R2, and we're going to tell R2 to respond, to give us stats about this traffic that we're sending to R2. It is super simple to set up, by the way. Let's go into global configuration mode. And I'm going to say IP SLA, and we're going to start an IP SLA operation. Well, actually, we're going to start the operation on R1. Here, I'm going to say I want to be a responder. IP SLA responder. That's it. That's all I have to do to make a router an IP SLA responder. So one command. And we can make sure that it's enabled by saying show let's type that correctly, show IP SLA responder. And it says we are enabled. Awesome. Now that we have something to collect our stats, let's send it some traffic. Oh, by the way, I should mention that IP SLA, it doesn't have to have a responder. We're not going to use a responder in our next demonstration when we're measuring or when we're making path forwarding decisions. We could say R1 just going to send out ping packets, and if the delay is too much, then we're going to go do something else. So we don't have to have a responder, but if you're looking for granular statistical information, you certainly should use a responder. So let's set up an IP SLA operation on R1 to send it traffic that looks strikingly similar to voice over IP traffic. Let's go into global configuration mode on R1. And let's create an IP SLA operation. We say IP SLA. Let me give some context sensitive help here. Oh, actually, before I type in the number, you see that we can give an entry number. That's going to be the operation. So we're going to say IP SLA 1. Now we're in IP SLA configuration mode. And what kind of probes can I send out? Well, I could just say voice over IP, but I want to be more specific than that. I'm going to say UDP echo because real-time transport protocol uses UDP. I'm going to say UDP, or not UDP echo, but UDP jitter. I want to measure the jitter of this voice traffic. UDP hyphen jitter. We're measuring that inter-packet arrival time. Now, using context-sensitive help, we need to put in the IP address. Well, this is the IP address of my responder. And you can see on screen that has an IP address of 203.0.113.2. I can say what UDP port number I want to use. And with this varies vendor to vendor, by the way, but Cisco, for their voice over IP traffic, they default to UDP port numbers in the range of 32768, 16384 through 32768. Actually 32767. RTP uses the even numbered ports, and there's a supervisory protocol called RTCP. It uses the odd numbered ports. Bottom line is a typical packet might use, we'll say 16384. That's the first available UDP port number that RTP might use. We'll just use that. And we can say, what codec do we want to use? A codec, that stands for a coder decoder, and that's how we can encode spoken voice into a bunch of ones and zeros. And there are different codec types available. We can use some context-sensitive help. And we've got G711, which is uncompressed voice. That takes up more bandwidth. We might, on a link where we're wanting to measure jitter, we're probably concerned about performance. We're probably not using an uncompressed voice codec. We're probably using something like G729A. So I'll say G729A. What else can we specify? We can say how big this voice packet's going to be. What is the codec size? Well, the default is 20 bytes. I'm going to leave it at that default of 20 bytes. And let's press enter. Let's see. Oh, what did I forget to do? Oh yeah, I forgot to say codec size. The codec size is going to be 20 bytes. There we go. Now we're in IP SLA jitter configuration mode. And from here, I can set the quality of service marking on this packet. See how granular we can be? I said that we can make this packet look strikingly similar to a voice over IP packet, right down to the quality of service marking. So what we can do is say, let me show you some of the other things we could set. What we're going to set is the type of service byte. And the type of service byte, this is a little tricky, because you might remember, if you've done any of your quality of service training with me, we talk about the fact that an IP header, IP version 4 header specifically, has a TOS byte, TOS, type of service, 8 bits. And we use the 6 leftmost bits in that TOS byte to mark a packet with a DSCP value, which stands for Differentiated Services Code Point. Go ahead and chat it in. Does anybody remember the default DSCP value for voice packets? Cisco IP phones do this by default. Do you know what it is? And I'll accept I'll accept 2 different answers, because these values not only have decimal numbers, they also have names. Well, the name of the quality of service marking that we give to voice packet is called EF, expedited forwarding. That has a decimal equivalent of 46. Now again, we're just looking at the 6 leftmost bits in that TOS byte. And if I'm looking at 6 bits and I want to make a decimal number of 46, that's going to be a binary value of 101110. However, here, we don't put in 46. Here, it's wanting the value of the byte, the 8 bits. And 46, that's looking just at the 6 leftmost bits. So I need to tack on 2 more zeros. That's going to give me a binary value of, I'm doing this from memory, so pardon me if I miss a bit, but that's going to give us 101110000. And if you convert that to decimal, that's not 46. That's 184. I told you this was not super obvious. So I'm going to say, I want to set the TOS value to 184, which really is a 46 DSCP value. Let's enter that. How often do I want to send these probes? I think I said I was going to do 30 seconds. You know what? Let's do 5 seconds. Let's be more aggressive about this. Let's say the frequency at which I'm going to send these is going to be every 5 seconds. Then I'll back out and I'll set a schedule for my SLA operation. I'll say IP SLA schedule, and it's going to be for my entry 1, my operation number 1, and I can say when I want to start this. I could say the start time is going to be now, and the excuse me, the lifetime, we'll just say, because I'll end this manually later, the lifetime is going to be forever, just to make it easy. So let's go ahead and enter that. And now every 5 seconds, router R1 is sending these UDP packets over to R2 that look strikingly similar to voice over IP packets. And after it's sent a few, we'll take a look at the stats that R2 is reporting back to R1. R2 is our responder. It's responding to those probes that we're sending from R1, and those responses are being tallied up in our IP SLA statistics. And you might have noticed I'm trying to kill some time right now while we're sending those probes. I think that's enough time though. Let's go and take a look at our IP SLA statistics. We can do that by saying show IP SLA statistics. And let's see if we have some meaningful information. It says, let's highlight this. 1 second. Whoop, clicked on the wrong one. Here we go. On R1, it says that we're using UDP jitter packets. The latest round trip time was 2 milliseconds. It's not bad. We can see round trip time minimum, average, and maximum. What else can we see that's interesting? We can see packet loss information, the jitter time. Now, I wouldn't be concerned about this outlier, the 999. That might have been the first one, or something might have got dropped. But our average jitter is only 2 milliseconds. That's and it tells us source to destination, and then destination back to source. That's averaging 1 millisecond. That's way less than 30, so I'm pretty happy with that. And remember I said that this would give us a mean opinion score. Anything above a 4 was considered to be toll quality. Well, check this out. Normally, G729A is supposed to have a mean opinion score of about 3.9 or 3.92, but here it's 4.06. So we've got toll quality in this isolated lab environment. That might have something to do with it. But that's an example of how we can send probes out and get statistical information about how the network is treating our traffic. Let's take a look at another example. Let me bring up another topology for you. And let me get over to my Linux PC for that. And let me share the new topology out with you. So here I'm sitting on the PC in this topology. And notice that router R1 has a couple of ways to get down to the server, which is on network 198.51.100.0/24. I could go via BB1 or I could go via BB2. Now right now I'm running OSPF in this network. And I did set the reference bandwidth, by the way, to a non-default value. In other words, it does know the difference between 1 megabit per second and 1 gigabit per second, which oddly OSPF does not know by default. But I set the reference bandwidth, so that's all taken care of. It's going to prefer to go to R2. I'm sorry, BB2, not R2. But R1's going to go to BB2, backbone 2, to get to the server because it's a faster link. However, what if that link became congested? What we want to do in this demonstration is say if that link is too congested, in other words, there's too much round-trip delay from R1 to BB2, then I don't want to go via BB2. I want to go via BB1. Now, before we do anything on the PC, let's just do a trace route to the server. Let's do a trace route to 198.51.100.3. and see what it's using, or see what router it's using to get to the server. The first hop, no surprise, is R1, 192.0.2.1. Where's it going next? Yeah, look at this. It's going to 203.0.113.5. If you take a look at the topology, you'll see that's BB2. That's not a surprise. That's what we expected. Now, let's create an operation that says if the delay between R1 and R2 is too great, let's go via a different path. Let's go to R1 to set that up. And let's create an IP SLA operation similar to what we did before. I'll say IP SLA, and we'll give it an entry number or an operation number of 1. And before I sent the type that I used was UDP jitter. This time, let's use ICMP echo, which is a ping. I'm going to ping R1 from R1 to BB2, and we're going to measure that round trip time. I'm going to say ICMP echo. And the destination, the IP address that I'm pinging is that ingress interface coming into BB2, which has an IP address of 203.0.113.5. And I want to source this from that incoming interface on R1 because that's the path being taken by the PC. I'm coming in gig 0/1 on R1, so that's going to be my source for this ping packet. The source IP is 192.0.2.1. Let's enter that. How often will I send these packets? Well, let's set the frequency to 5 seconds again. Now we can say how much is too much. We can set a threshold, and we can say if the round trip time is above 100 milliseconds, then we're going to do something different. We're going to go to a sort of a down state. So let me show you how this works. I'm going to say threshold, and the unit of measure is milliseconds. I'm going to say if I exceed a 100 millisecond round trip time, that's going to go over my threshold. And that's going to cause me to use an alternate route. I'll show you how that works in just a moment. But now we need to set the schedule. When's this going to run? Just like we did before. I'll say IP SLA schedule for operation number 1. The lifetime is forever. Start time is now. So let's start sending those packets. Now, here's how we can make this route go away if our condition is no longer met. We're going to use something called a tracking object. We oftentimes use tracking objects when we're setting up first hop redundancy protocols like HSRP. But here's how it works. I'm going to say track, and I'm going to give it an object number, an identifier of 1. And what I'm tracking is the state of IP SLA operation or instance 1. And if we violate the threshold of 100 millisecond round trip time, then this tracking object is going to go down. Now, here's a best practice. If I have the odd packet that gets dropped, I don't want to have route flapping going back and forth between BB2 and BB1 just because I dropped 1 or 2 packets. So normally what I'll do when setting up a tracking object is say, I'm only going to do this, I'm only going to take this route away and start using another route if I have been in this down state for over, let's say, 10 seconds. So I'm going to insert some delay here. I'm not going to do it immediately. If I drop 1 packet, I'll give it some grace and I'll wait to see if it keeps happening for 10 seconds. So I'll say, I'm going to delay going between a down state and an up state for 10 seconds. So I have to be down for 10 seconds before I'll actually go down. And then maybe the odd packet comes through that is less than 100 milliseconds. Do I immediately go back up? Well, again, I don't want to go back and forth, route flapping. Cisco gives that a name called hysteresis. I'm going to say, I want to make sure that we are consistently below 100 milliseconds, below our threshold, for 10 seconds before I'll come back up. So that's our tracking object. Now, what does that tracking object, how does that affect our routing table? Well, I'm going to use a couple of static routes. I'm going to override OSPF, and I'm going to create a static route that says, hey, if you're trying to get to 198.51.100.0/24, go to BB2 if the tracking object is up. Then I'll create another static route that has a slightly higher administrative distance than the first static route. That's going to kick in only if that tracking object is down. Let me show you. I'm going to create a static route that says, go to BB2 if you want to get to that network on which the server resides. I'll say IP route, and that's for network 198.51.100.0. And it's a 24-bit subnet mask, 255.255.255.0. And I'm going to go to a next hop of 203.0.113.5. That's BB2. Now, here's where I add the qualifier. I'm going to say track 1. I'm saying use this route if and only if tracking object number 1 is up. What makes tracking object number 1 up? we have a round trip ping time that is consistently less than 100 milliseconds. If that condition is not met, then I'll not look at this route. I'll look at another route that I'm going to define now. Remember the default administrative distance for a static route? It's 1. Well, I'm going to create a static route that says, oh, you want to get to that network of 198.51.100.0/24? Go to BB1. But I'm going to give it an administrative distance of a 2. It's less preferable than this one that I just gave. But if this one disappears because the tracking object goes down, snap, that other one's going to show up. I'll say IP route 198.51.100.0, 24-bit subnet mask. Let's go to 203.0.113.1. That's BB1. Now I'm going to give a number of 2. That's the administrative distance of this route. We're not going to use this route as long as the previous route is up, as long as tracking object number 1 is up. Let's see what we're using right now. Let's do a show IP route command. And you see that we have, let me highlight it for you, this static route to get to 198.51.100.0. It says we're going to go to 203.0.113.5. Notice this static route has an administrative distance of a 1. Now, this is up, or this is in our routing table because tracking object number 1 is up. I can prove that it's up by saying show track 1. And it says very clearly that the state is up. It tells us the latest round trip time was 4 milliseconds, well below 100. We got no worries there. But let's say it did exceed 100. What's going to happen then? How can we test that? Well, the way I'm going to test it is to make that threshold much, 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 much lower. I'm going to set the threshold to 1 millisecond. And I think we're going to be consistently exceeding that. I'm just going to do that not because it's a realistic threshold, but I want you to show you that we can fail over to this backup path. Now, unfortunately, I'm not able to edit an IP SLA operation that I've already started. I have to delete it and then put it back again. So I'll try to type quickly here. Let's go into R1, and I'm going to get rid of our existing IP SLA operation. I'm going to put it right back. I'll say IP SLA 1, ICMP echo, going to 203.0.113.5, pinging BB2 from a source IP address, that incoming interface on R1 with an IP address of 192.0.2.1. And we're going to send these pings out every 5 seconds. But this time I'm going to set the threshold to a almost unachievable 1 millisecond round trip time. Yeah, I don't think that's going to work. So we'll probably have a tracking object that's down. And I'll say IP SLA schedule for operation number 1. The lifetime is forever. The start time is now. Now let's give it more than 10 seconds and we'll check the state of our tracking object. Let's do a show track 1, and it says the state is down. Why? Because my threshold was only 1 millisecond and I'm averaging about 4 milliseconds. So if I look at my IP routing table now, if I do a show IP route, scroll down here, notice my static route now points to 198.51.100.0. It now points to 203.0.113.1. That's BB1. And you notice this has an administrative distance of a 2. So because that tracking object went down, which was because our IP SLA operation sending out those ping packets measured a round trip time less than our threshold, which was admittedly unachievable in this case. But in the real world, you might set it to something like, I don't know, 15 milliseconds, depending on what you're trying to do. It made that one route disappear and the other route show up. Let's see if this is really working. Let's go back to our PC where we started. Let's see, I've got lots of tabs open here. All right, there's our PC. Let's do another trace route. Now before, you notice that I went to a .5 here, that's BB2. Let's see if we now go to .1 as our second hop, because that would be BB1. First hop is going to be R1. Now what are we going to get? Oh, look at that. It's .113.1 this time. That's BB1. What we did was override what OSPF was telling us. OSPF does not know about delay. It doesn't know if a link is congested or not. It's using cost, which is a function of bandwidth. And from that perspective, the link between R1 and BB2 looks a lot more attractive. But we overrode that because maybe we had a suspicion that this was going to be an issue. We overrode that with an IP SLA operation. And that said, if we exceeded a round trip time to our default gateway or our next hop router, we're going to use a different next hop router. So that's a look at a couple of different ways that we could use IP SLA. We saw how we could use it, what I call IP SLA RTR, where we're sending to a responder and it's giving us statistical information. And we saw how we could use it to make routing decisions with the help of a tracking object. Hope you enjoyed those demos. Now, we're going to take another little breather, another break. Welcome back from our second and final break as we take a look at our third of three advanced routing techniques that we're going to be talking about today. And if you joined us late, let me remind you that if you stick around to the end, I'm going to give you a link where you can download resources from today's session. It's a zip file that contains PDFs. Those PDFs have the topologies that I've been showing you. It's got the base configuration for the routers in those topologies, so you can set this up on your own gear. It's got a complete walkthrough script of the demos that I've been doing for you. And if you happen to be running CML, I'm including the YAML files as well that you can import to maybe save you a few minutes as opposed to setting it up using those base configurations. YAML files, they work a percentage of the time. If they do, great. If not, you've got all you need to set it up on your own gear. Now, let's get into our third topic, which is policy-based routing. This is where we can override what the IP routing table or the CEF fib table is telling us about how to forward a packet. We can set up a rule. Here's the way that routing traditionally works. We've got a packet coming into router R1 here, and it's going to take that frame, that layer 2 frame, it's going to look at the frame check sequence to make sure it's not corrupt. It's going to remove the layer 2 header. It's going to take a look at the IP addresses, the source and destination IP addresses inside of that frame and the packet. The packet header, and based on that, it's going to check its routing information like the CEF fib, and it's going to decide how to forward that packet. Maybe it goes out over the top link in this case. If we don't want that to happen for specific traffic types, we can override that on a sort of a case-by-case basis. We can identify traffic with an access control list and say, if you match this access control list, I want you to go a different way. We can do that with PBR, policy-based routing. Here we've got a packet coming into our router, and we again take a look, make sure it's a valid frame. We check the frame check sequence. We remove the layer 2 header. But before we make that routing decision, as we're taking a look at the source and destination IP addresses and the ports, if we match this access list and we have a policy for traffic that matches that access list, then what we can do is use that policy. And that policy might say, all right, I want you to go out the bottom link based on our route map instructions. That route map, we've set a couple of those up today already. One of the we used it for a tag and to set a metric value. Well, we can use it now to set a next hop IP address to override the IP routing information in our router. And the route map, we've used it a couple of times, but let's dig into it just a bit deeper. We don't always have to match something. If I want to apply this to all traffic, then I can just set a parameter. I can set a tag. I could set a metric. I could set a metric type. I could set a next hop IP address. But we could match traffic based on things like the IP address, using an access control list. We could do it based on packet length. There's a variety of ways that we could match traffic. But once I match traffic, then I could set something like go to this next hop IP address, or here, go out of this interface, or here's the default interface you're going to be using. Let's demonstrate this using an identical, this is not the same set of routers, but it's an identical topology to what we were using just before our previous break, which used this topology, I'm sure you'll remember, but this is just another instance of that topology. It doesn't have the configuration we gave before the break. What we're going to be doing here is creating a policy that says if traffic is coming from the PC to the server, then I don't want it to go its normal path. Remember, I'm running OSPF here, and OSPF is going to prefer that faster link from R1 to BB2 to get to the server. Let's say that link we've determined it's faster, but it's not as secure. And maybe we've got some really secure traffic, or maybe it's not as reliable. For some reason, the specific traffic coming from the PC to the server, we want it to take an alternate path. We want it to go from R1 to BB1 to the server. Let's see what path we're taking right now from the PC. Let's do a trace route to the server, which is 198.51.100.3. The first hop is going to be that ingress interface on R1, which is 192.0.2.1. Now, let's see where we go. I'm guessing, we went to BB2. BB2 has an ingress IP address of 203.0.113.5. If that were .1, that would be BB1. But OSPF said, you know what, I'm going to go the gig link because it's faster. It has a lower cost. Let's override that only for, not for everybody, just for traffic, because let's say we've got a specific need, that we've got knowledge that it's a more reliable link to go to BB1, or there's less jitter on it, or there's less, something's better about it. Maybe it's more secure. It's more, it goes through a data center instead of under somebody's floor in their office. We want to use that path just for this super sensitive traffic coming from the PC. So first up, I'm going to create an access control list that identifies just traffic from the PC to the server. Nobody else is going to be impacted by this. Let's go into global configuration mode, and I'm going to create an extended access list. I'll say access list, I'll give it a number of 100, and I want to permit all IP traffic coming from a host, a source of 192.0.2.2, that's the PC, going to a destination, which is a host of 198.51.100.3, that's the server. Now let's create a route map that is going to match traffic that matches that access control list. Let's say route-map, and let's give it a name. Again, I like to use all uppercase naming. I'll say client-to-server. That'll be the name of my route map, and I want to match IP addresses that match the access control list that I numbered 100. And what am I going to set for that traffic? Specifically, what am I going to set for traffic coming from the PC to the server? I want to set the next hop IP address. Not to BB2, but to BB1. I'm going to override what OSPF is doing. I'll say I want to go to a next hop just for this traffic that matches the ACL. I want to go to 203.0.113.1, not .5. And now let's apply that route map to traffic as it comes into that gig 0/1 interface on router R1. That's where we want to apply it. So let's go into interface gig 0/1, and I can apply this policy by saying IP policy. I want to use a route map that I named client to server. Now let's go back to our PC and do another trace route. What is going to be my second hop? Is it going to end in a .5? Hopefully not. Hopefully it's going to end in a .1. Let's take a look. Yeah, look at that. 113.1. That, my friends, is BB1. And for all of our other traffic going to the server and coming in router R1, everybody else attached to switch 1, in other words, everybody else is still going to go from R1 to BB2 to the server, but not the PC, because it matched an access list, which we matched using a route map, and we use that route map to create a policy to set its next hop IP address, and we applied that policy to that ingress interface on R1. And that is a look at policy-based routing. Hope you enjoyed that demonstration. So what we've done today is we've taken a look at 3 different advanced routing technologies. We took a look at route redistribution. We even saw how various ways that we could do troubleshooting of route redistribution. We also took a look at IP SLA, RTR, which is where we have a responder and it collects statistical information. We also had a demonstration of IP SLA where we used it to make a routing decision, and we saw how we could use policy-based routing to also make a routing decision. And as promised, I said I would give you a download of the resources from today's session. So if you want to, you can do this on your own. Here's the link for you. Go to kwtrain.com/AR-download. AR for advanced routing. So kwtrain.com/AR-download. And you'll get that page where you can click the button to download a zip file. And in that zip file, you'll find a bunch of PDFs, one for route redistribution, one for the IP SLA RTR demonstration, one for the IP SLA path selection demonstration, and one for the policy-based routing demonstration. Each of those PDFs will contain the topology diagram, the base configs for all the routers so you can set it up on your own gear, and a walkthrough script of what we did today. And I'm also including, just for fun, YAML files of all these topologies. So if you happen to be using CML and it's compatible with CML version 2.6, which is what I use to export those YAML files, it might work. YAML files don't work 100% of the time when you try to import them into different versions of CML, but who knows, it might. If it doesn't, no worries. You've got all the base configs in those PDF files. But just go to kwtrain.com/AR-download, and that'll get you your resources.